Okay. Um, uh, Thank you for having me in this wonderful workshop and giving me an opportunity to present my work. This will probably be the only zero temperature talk in a finite temperature conference. Yeah. Um, so, um, so this is based on some work that we put out recently with my collaborator Luca and Umang. Umang is a postdoc at University of Colorado Boulder. He's moving to University of Minnesota this fall. And Luca is a faculty at the University of Chicago. Um, so this will be somewhat the outline of my talk. So I'll first motivate the problem that I want to study. Uh, then, like, I'm assuming that a brief review of Fermi liquid theory would be of uh, interest to people. Then I'll like put symmetry and causality constraints on the on a effective field theory of Fermi liquid. I'll also discuss nonlinear response using this effective field theory and also put constraints on it. And finally, I'll end with some open problems that we have been thinking about. All right, so conformal field theories are of interest in both high energy physics and condensed matter physics. And while I don't need to explain like why it's of interest to high energy physics to the audience here, I'll try to motivate a more condensed matter point of view, in the sense that it is kind of conventional to think of doping a conformal field theory to generate new IR phases of matter. What do I mean by that? So consider a conformal field theory at finite chemical potential. You add this deformation to conformal field theories. This is a relevant deformation, which triggers an RG flow. And in the IR, you can have a whole spectrum of like compressible phases. By compressible phase, I mean that these have gapless excitations, okay? You can have superfluids when this the U1 symmetry here is spontaneously broken. As we all know, the effective field theory for such superfluids is described by the Goldstone boson that arises because of it. You can also have conformal solids, and by the way, like this has been like this is has been studied very widely as to like from conformal field theories, how do you recover relativistic superfluids in the IR? Okay. You can also have conformal solids, like where because where you break both translational as well as rotational symmetry in the IR, and your IR phase organizes itself into some sort of crystalline structure. And this was postulated by Subir Sachdev in a very nice paper, where he claimed that the standard O2 model for the CFT corresponding to the standard O2 model, after some fine tuning, you can achieve such a conformal solid phase. And there has been like numerous holographic also like studies regarding this, okay? And there is also another very interesting phase, which is that like when the U1 symmetry is unbroken, the translational rotational symmetries are also unbroken, but instead you have a Fermi surface developing in the IR, and such Fermi liquids from conformal field theories have also been studied by Gerasi, Son, and Gyokman. Okay, right. The question that I now want to ask is that can we get any compressible IR phase in this manner? What do I mean by this? So all these phases, the IR phases that I described to you just before, they are described by some sort of effective field theory. As we all know, effective field theories have irrelevant operators, which are the Wilson coefficients in the effective field theory. My question is, can these Wilson coefficients take any value? Okay, and gapless, gapless excitations. That's it. Yeah. So the answer is no, and I will show you that at least for Fermi liquids, symmetry and causality of the underlying microscopic theory severely constrains the EFT parameters that arise in these effective field theories. Okay, and this is motivated. This is motivated by emerging new trend in at least high energy theory, where people study like UV IR type of constraints in effective field theories. Now, for a long time, people have just been interested in like relativistic QFTs in relativistic vacuum. But more recently, people have begun asking this question in also like states which break Lorentz invariance, namely like the thermal state as well as the finite density state. So today I'll be focusing on one such finite, sorry, what's the question? I'll be focusing on one such finite density state, which is Fermi liquid, but I would also encourage you to look at this set of papers by Paolo Creminelli and collaborators who have also done this exercise for superfluid, relativistic superfluids. Okay. It depends on the Wilson coefficients. I'll show you some plots. Yeah. Yeah, we don't want to rule out, for example, the critical O2 model. I mean, that also has a superfluid phase, so we don't want to rule that out. I'll show, for example, in context of Fermi liquids, I'll show that the Wilson coefficients, there is an allowed region where, if you have a CFT which admits a Fermi liquid phase, it should lie within that region, the Wilson parameters, and I'll show an explicit example like Son's CFT, like which he studied, that is allowed by causality. Okay. So Fermi liquids are interesting in their own right. These is one of the most prevalent finite density states in nature. Uh, like it describes, like from condensed matter to high energy physics, it describes liquid helium, as well as it's relevant for studying like high density phases in QCD, as well as dense neutron stars. So, and phenomenologically, like also like these are very different from like the other types of compressible phases that I showed you. For example, one of the striking observations is that at low temperatures, the specific behavior of specific heat is proportional to temperature rather than like T squared for a conformal field theory in 2+1 dimensions. It also has somewhat large entanglement entropy, which might be clear once I start explaining like the degrees of freedom. And also like it has unbroken U1 translations and rotations. So in general, like an effective field theory for such a phase is somewhat difficult to write down because you don't have it's not easy to find the Goldstone mode for such a system, basically. Okay, traditionally we studied as like particle hole excitations. Right. Okay, so I'll just give you a lightning review of a refresher of your Fermi liquid theory. So imagine like we consider free non-relativistic fermions. This is in a box. You solve the many-body Schrodinger equation, you get quantized eigenvalues, and you plot them in this plane. You find that because of Pauli exclusion principle, like two particles cannot have the same kx and ky integer values, and as you increase the number of fermions, like you fill out this Fermi sphere, which is the with the radius given by the Fermi momentum, which also sets the Fermi energy. Okay, The many-body wave function for this is very easy. It's a Slater determinant of just the free fermion wave functions. And usually instead of the many-body wave function, it's convenient to describe the state with a density distribution which takes value 0 if P is greater than the Fermi momentum, or it's 1 if P is less than the Fermi momentum. Okay. Now, once we have this, then we can have. By the way, please stop me at any point, like to ask questions, clarifications. So we would like to study the excitations about this ground state. The excitations about this ground state are particle hole excitations. You pull out an electron from this C, it leaves a hole, and this is the spectrum that you want to study, we want to study. And this and all the possible such excited states you can model by looking at the smooth deformations of this spherical Fermi surface. So these excited states can be thought of as these fluctuations of this spherical Fermi surface. And since I'm assuming that there are no collisions, I'm at 0 temperature, the time evolution of this spherical Fermi surface into these fluctuating shapes is described by the Boltzmann kinetic equation. Okay, where F is this F describes this fluctuating shape. H is the Hamiltonian. This is the quasi-particle density, and V would be some external potential that you would apply. Okay, and it has this initial condition that at time t equals 0, you must have the spherical Fermi surface. Okay, right. Now, once you, so this was the free picture for free theory. Now you start adding in interactions. So the beauty of Fermi liquid theory is that it's an effective field theory in the sense that you turn on the interaction diabetically and the degrees of freedom remain unchanged. Okay. Instead, like the ground state of the free theory continues to be the ground state of the interacting theory up to some caveats. The caveat being that like this entire picture remains valid when we are looking at only very small excitations, okay, about the Fermi surface. And in presence of interactions, the only thing, therefore, which changes in this entire in the Landau kinetic equation is that instead of like this the quasi-particle energy of the free electron, you now have a modified energy functional, which encodes how the quasi-particle, like the experiences forces from other surrounding electrons in your system. Okay, so this is what is traditionally called the Landau parameters. These are the Wilson coefficients of our effective field theory, and contrary to like usual relativistic effective field theory, for example, like you can see that already this is like, it's an entire function of momenta rather than being just some number that you can evaluate. So already things are looking a bit complicated. You have basically infinite set of parameters here, basically, okay? Even at this level, okay? Okay, so now this looks like a effective field theory. This feels like an effective field theory, so therefore it must be one. And indeed, like this effective field theory, you can organize it as an expansion in 1 over Fermi momenta. And effective and attempts to describe Fermi liquid theory as an effective field theory is not something new. It dates back to Polchinski and Shankar in the 90s, but my collaborators and Son and Ishin in 2022 formulated a new EFT which describes the Fermi liquid theory in terms of the phase space density rather than, like, say, fermion excitations, which Polchinski tried to do. Okay, so they wrote down an effective field theory of shapes, basically like telling us how the shape, how the action basically told us. You can derive the Landau kinetic equation from this action, and it basically tells us how the shape changes. Okay, and what they observed is that for low enough energies, these fluctuating shapes are obtained as canonical transformations about the spherical ground state. Okay, um, so if this was too much information, forget about it, because uh, I won't be needing like the explicit how they explicitly derive the action so much. I'll just give you the answer, and like I'm sure that will be enough for my purpose. Good. So they are working in this phase space formalism. So normally, like, you would work in, say, so you would have something like, so you would have something like this, and this would be like some psi dagger k1, psi minus k1 on Fermi surface, right? That's how this thing. But they're working in a system where they're working in an equivalent way of representing this excitation is to Fourier transform along the relative momenta. Okay, this is called, if I'm not wrong, Wigner transformation. So instead of K1, K2 space, like, they are expressing this in terms of X and P space. Okay, so it's basically like, instead of this, like, so you can think of this excitation as some sort of like a deformation of the spherical Fermi surface in XP in the phase space, basically. So these excitations are basically these deformations of this Fermi surface in the phase space. Okay. I'm just, I have not drawn like the X space, but like it's understood that, like, at every point, like, you have some Fermi liquid, some Fermi sphere, which are fluctuating. Okay, so that's the idea. Yeah. Okay. Uh, right. So, then, like, so building on their idea, like, so what they, so you might ask, like, okay, then, like, if this is given by some canonical transformations, like, how does this look like? So, as I showed you, like here, for example, these deformations of the spherical Fermi surface, they can be parameterized in terms of this exponential phi function. Okay, this is just how they choose to parameterize it. And then a most general distribution function at a given point in time takes this form, where these are like the Poisson brackets of these are the Poisson brackets. Okay, um, and also, in general, this function phi, which generates these fluctuations, they can be like of any form. Like, they can be a function of time, space, and momenta. But there is a restriction on this, which is the fact that not all canonical transformations give you the same state. So, for example, some of the canonical transformations will just keep your sphere the same. So you don't need to consider them. And what effectively it boils down to is that, like, this function now just depends on the angle on the Fermi surface. This is some gauge fixing condition that results because of this restriction. Okay, and finally, like what you would, the Gaussian action, which we want to look at initially, is given by this, where phi is this field phi, and F20 was our Landau interaction, but now we restrict to like, so it's basically restricted to the Fermi surface. So in some sense, it's P prime is given is like kf theta kf theta prime, like I mean the n theta prime n. Okay, so it's like it's the modulus of the momenta is fixed and it's just varying across the Fermi surface. Okay. So now, so basically, we have an action which describes fluctuations of hormone. Yeah. 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 Collision free. Yeah. No. No. Yeah. I don't have a good answer to that. I thought about it, but uh, I think the formalism kind of breaks down if you try to include collisions. Uh, I think so, because I mean, the entire premise of this construction was that like the sharp Fermi surfaces remain sharp. And the only way that happens is that when you don't have collisions. So I'm not sure like how if it's a immediate like, small improvement on this kind of formalism. Like you might have to think about like, uh, I'm not super sure you can do that. But like we can chat about it later, maybe. Because anyways, like I won't be talking about, I'm working in the limit where I don't have any collisions. So for now, like, let's forget about that, but we can chat later. Okay. Okay, so now I want to ask the question that fine, like this is an effective field theory. There must be some UV theory which leads to this IR phase. So if the UV theory has conformal symmetry and Lorentz symmetry, how are these imposed in our action? Now, remember that like the way I broke the Lorentz and conformal symmetry is it's a spontaneous breaking of the symmetry, because I'm just evaluating my regular CFT in a finite density state. Uh, and so in general, like the transformations of these fields that I showed you in the previous slide, the symmetries would be non-linearly realized on them, okay? And in general, like trying to figure out like how how the non-linearly realized Lorentz and conformal symmetries work out in phase space is a difficult thing to do. So for the moment, how what we'll do is that we'll try to constrain correlation functions using the EFT, compute them using the EFT, and then use symmetry principles to constrain the correlation functions, okay? So the observables that we want to look at are correlation functions of conserved operators, because that's the easiest to match in the UV and the IR. They are not renormalized. So, this is the density operator to linear order in the fluctuation phi, and this is the momentum current to, again, to linear order in fluctuation phi. And and the way you get this by is you take our action and you couple it to some background gauge field to get the density. And since my action, oh, by the way, like this action is like translationally invariant as well as rotationally invariant, So you can do another procedure to generate the momentum current from our action. Okay. All right. So just to warm up, let me try to ask the question like what happens when the UV theory has Galilean invariance. Okay. Now, Galilean invariance is, of course, of very, it's realized in liquid helium. So we just want to make sure that like we recover the usual constraint by Landau using this methodology. So the thing that we want to look at for this case is the zero frequency and zero momenta limit of the retarded correlator of momentum density. Uh, so from the Gaussian action, you can turn on sources and you can actually non-perturbatively compute this, this susceptibility, where I have decomposed my Landau parameters in terms of these Wilson coefficients, these harmonic functions, and these L's run over from 0 to infinity. Okay. So there is an infinite amount of data that is already encoded at the Gaussian action. Okay. And then on the other hand, what we can ask is that like whether we can use some symmetry properties of the microscopic theory to actually compute this correlator. Now, for Galilean invariant theory, there is this word identity, which is that the momentum current is proportional to the charge current. Using that, you can actually compute this correlator using this identity, and then we equate both these sides to get Landau's constraint, which he derived by explicit Galilean transformations in the Landau kinetic equation. Okay. Here, M is the bare mass or the central charge of the Galilean algebra. This is some UV constraint and UV data. And okay, so we are happy with this. So now, how do you impose Lorentz invariance? So we switch gears and we want to actually ask how do you impose Lorentz invariance, because we want a relativistic as well as conformal, we want a conformal Fermi liquid. Okay. So the left-hand side remains the same, but now we have relativistic word identities, which are these, where you think of this as evaluating these word identities in finite density states. And it's somewhat of a bit of a computation. It involves some subtlety regarding like contact terms and so on. But one can again show that using just these relativistic word identities, the momentum susceptibility is actually fixed in finite density relativistic field theories. Okay. Yeah, and that's equal to mu plus mu rho. Yeah, that was yeah. So this paper, and then there was a very nice lecture note by Chris Herzog, like where he showed that like for this using this relativistic word identity, you can actually show that epsilon plus p is equal to mu rho. So I'm at 0 temperature. Yeah. So using that, like you can basically do this. And then you have this constraint. And this was actually first discovered by Gordon Baim and Chin in 1976. But they explicitly used they use transformation properties of the quasi-particle energy density in deriving this, which for the linear order is fine, but as I'll show that moving beyond linear order, it's very difficult to like figure out like how the transformation will be. Okay. Okay. So then like we can also go for we can also try to impose scale invariance, which and the observable for that is the charge susceptibility, which is the low frequency limit of the density correlator. Okay. You can do this computation in the Gaussian action. It constrains F0 of the Landau parameter. And then like, so I have here kept a dynamical exponent Z the 1-point function of the row density, because mu is the only scale in the problem, it behaves in this way. And then you can actually follow through the steps to get like the charge susceptibility for a arbitrary z dynamical exponent. Okay, and then then equating both the sides, we find that the f0 component of the Landau parameter is actually constrained by this, is actually constrained, okay? And so for example, for z equals 1, one recovers the usual non-relativistic scale invariance, while for z equals 2, it is part of this Schrodinger invariance that happens in, for example, cold atom systems, okay? Right. Okay. So, so one more point, which is that like, so we have imposed scale invariance and Lorentz invariance. Now, from these two expressions, you can see that for a conformal Fermi liquid, you can actually solve for VF in terms of these two parameters. So VF turns out to be 1 over square root of 1 plus F0 times 1 plus F1, okay? So this is an exact relation like for conformal Fermi liquids. Yeah. So the way we are now here imposing the condition is that like we have the non-relativistic action, and then we are imposing symmetry constraints on the action. So if it was non-relativistic action, these VFs and Fs would not be related. But because we are imposing relativistic invariance, they become related. Of course, you can try to write down a explicitly, manifestly Lorentz invariant bosonized action, which we were not able to do using Son's or Lucas formalism. The coadjoint orbit formalism is somewhat inherently non-relativistic. So yeah, yeah. That's the problem. So then, like, it's quite difficult to, yeah. Yeah, that's the entire reason why we had to do this circumnavigating this entire thing. Yeah. Okay. Okay. So now we want to, I want to study causality constraints because I have a UVCFT which is causal, and okay. And as we know that like causality implies for space like separated local operators that the commutator must vanish. And this implies that the retarded Green's function, which when it's polynomially bounded, must be analytic in momentum space for support on the forward light cone, okay? So this immediately means that all the non-analyticities in my retarded Green's function must appear in the must obey this condition. This has been used several times in the workshop. So I think you guys don't need any introduction to this. Um, so so then like how do we go about this? So one of the first things that we notice is that like, even if you consider the free effective field theory and you compute the retarded Green's function of charge density, it has non-analyticities, okay? And this source of non-analyticity is somewhat physical, which is that this variable S, which is this guy, this denotes the start of particle hole continuum. So for S less than 1, it's basically like you're going into particle hole continuum, and that's like a branch point in the retarded Green's function. So causality therefore implies that VF must be less than 1. And for conformal Fermi liquid, since we can exactly solve for VF, it turns out to be this following condition on the Landau parameters, okay, on F0 and F1. Okay. Okay. So we can also have, since this is an interacting Fermi liquid theory, we are not like restricting to weak coupling. It can be strongly coupled. You can also have collective excitations. Okay, these are traditional. These are famously, for example, like helium. Liquid helium has this zero sound mode, which is so we obtained like similar collective excitation modes for our system. Now, for simplicity, we consider that the higher order Landau parameters are set to 0, but you can actually solve for these sound modes irrespective of how many Landau parameters are turned on. You'll just get more and more modes which are non-dissipative, basically. Okay, so and this is a plot of the basically like the analytic properties of the Green's function. So here we have the particle hole continuum and the zero sound and the shear sound, which is another type of this kind of collective excitation. These are distinctly separate from the particle hole continuum. Okay, and we therefore like these and these collective excitations, if you actually solve the, if you compute the Green's function, they appear as poles in the Green's function. So therefore, they must also satisfy this non-analyticity criteria that I told you before. Okay. So these are the criteria, and so because we are, yeah, I don't have a physical picture of it, but it's just basically like because you turn on two Landau parameters, there are basically two collective excitations that come out of solving the interacting Landau kinetic equation. I'm sure there is a more physical picture of it in terms of deformation of the Fermi surface, but I'm not super sure of it. Like, yeah. So zero sound, for example, is like this kind of weird deformation of the Fermi surface along the equatorial region, but I don't know how the shear, how to visualize the shear sound. Okay, yeah, 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 yeah. Mm-hmm, mm-hmm. Yeah, 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 yeah. Uh-huh. Yeah. So yeah. So the only comment I would have is that we are looking at the low energy excitations. Um, for the low energy mode, these are the only excitations that you have. You have the collective modes, and then you have the modulation of the VF due to the due to the Landau parameters. There is nothing else here. Yeah, but yeah, I mean, away from small momenta, and we don't have a very good, yeah. Hmm. Hmm. Yeah, I I think this is kind of non-perturbative. This this kind of like 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 the structure like so first of all like these are marginal interactions. So like we already have taken into account that you have actually summed over everything. You might ask, like, what happens if there are other Landau parameters? But like the usual Landau parameters that are there, they have been all taken care of. Right? Because so one of the way you can think about it is that, like, you can try to solve the Landau kinetic equation, like look at the non-analyticities that you just get by solving the Landau kinetic equation. Okay, there is this one point, which is that for s less than 1, you have particle hole continuum. So that's like one source of non-analyticity. And then you just have this pole like this thing. This is just by analyzing the Landau kinetic equation. And this should just be these should be the only thing which appear in the Green's function, because we are just, this is just, I'm solving it non-perturbatively, right? Just by looking at the poles. So for example, like the one way to see this is that, like, this relation between VF and the Landau parameters, it's completely non-perturbative. Like it's basically VF is for example, like 1 over square root 1 plus if